The ocean is a physical environment that exposes every structural weakness. Surviving it requires engineering for the constant, violent forces of the open sea. But long before the first steel plates are welded together in a shipyard, the journey of a modern vessel begins in a quiet, climate-controlled office. In this space, a ship capable of carrying thousands of tons exists only as a digital model, bound by the laws of mathematics, operational requirements, and strict budget constraints. Every calculation must be proven in simulation. A vessel built without adhering to these initial physics models would become a liability rather than a functioning maritime asset. Before a single piece of steel is cut, the ship must conquer the elements theoretically. Transforming an idea into a physical vessel requires a cyclical methodology known as the design spiral. In this loop, no decision is made in isolation. The hull shape dictates the ship's stability, which influences the required structural framework. This framework changes the vessel's overall weight, which then cycles back to affect the stability once again. Because these parameters are interdependent, a minor miscalculation made early in this process can cascade through subsequent stages. A small error often forces engineers to restart massive portions of their calculations to prevent structural failure. This relentless refinement is the only way to balance the vessel's safety, its fuel consumption, and overall cargo efficiency before the design leaves the digital realm. To define the shape of a ship's underwater body, architects calculate the block coefficient, or CB. This is the ratio of the ship's actual immersed volume compared to a rectangular block of the exact same length, beam, and draft. This oil tanker has a high block coefficient. Its wide, full hull form maximizes cargo capacity, operating at slower speeds to move more volume. A slender naval frigate, however, has a low block coefficient, prioritizing speed and agility over maximum capacity. Many modern ships utilize a bulbous bow, a streamlined protrusion situated just below the waterline. This concept was applied to the USS Delaware in 1910. Testing and towing tanks refined this feature into a tool for wave cancellation. The protrusion creates a secondary wave trough that coincides with the crest of the ship's natural bow wave. This destructive interference cancels the wave out, reducing fuel consumption by up to 15%. The ship's outer skin is a deliberate geometric shape, calculated to minimize resistance by neutralizing the water it displaces. A ship's ability to stay upright depends on intact stability, the capacity to return to an even keel after being tilted by wind or heavy waves. This relies on two interacting points. The center of buoyancy pushes upward from the center of the displaced water, while the total weight of the ship acts downward through the center of gravity. The theoretical pivot point above these forces is the metacenter. The vertical distance between this point and the center of gravity is the metacentric height, or GM. If the GM is too large, you get a stiff ship that snaps back upright so quickly it can damage cargo and injure the crew. If the GM is too small, the ship becomes tender, rolling slowly and lacking the righting energy to prevent a capsize in heavy weather. Achieving stability is a calculation that balances these two physical risks, ensuring the vessel can safely manage the energy of the open ocean. Underneath the exterior geometry is a steel skeleton engineered to endure continuous mechanical stress. Primary strength comes from the framing system. Transverse framing uses vertical ribs spaced closely together. Longitudinal framing uses stiffeners running the length of the ship, which prevents the hull from bending under the weight of its cargo. This framework integrates watertight bulkheads to divide the ship into secure compartments, and a double bottom that creates a mandatory structural gap between the outer hull and the inner tanks. These scantling calculations result in a ship within a ship. This separate, hollow structure is designed to absorb the impact of running aground without compromising the integrity of the inner cargo holds. These designs must navigate a final set of external constraints, the Maritime Regulatory Framework. Independent bodies known as classification societies, like Lloyd's Register, establish and enforce the rules for ship construction. Surveyors from these societies must approve every drawing, calculation, and stability curve. Without their certification, a vessel cannot be insured, which legally prevents it from engaging in international trade. The engineering work completed in the design spiral is only verified once it meets these external safety and environmental standards. When the final design is approved, the data is transmitted directly to computer-controlled cutting machines in the shipyard. Historically, ships were built on a slipway, an inclined ramp where the vessel was constructed and eventually launched backwards into the sea. Modern construction usually takes place in a dry dock, a massive basin pumped dry, allowing workers to assemble the vessel on a solid floor. An empty graving dock, excavated into the earth and sealed by watertight gates, waits for the transition from digital blueprints to physical steel. While the physical ship has not yet been built, its performance is already determined by the accuracy of the naval architect's mathematics. Join us in the next episode as we leave the design office for the shipyard, where these calculations are forged into a physical reality.